Hello, this is Exponents and Logs, lesson number 1. I hope this makes sense for you. Standard disclaimer, please make sure you're attending class, as in class we will go through this in much more detail. However, nonetheless, let's get going. So Exponents and Logs, lesson 1. Okay, there's quite a bit involved in this unit. Now, where I want to start with, because this is absolutely the beginning of this unit, what's the end goal? What's the purpose? This unit, okay, as you can read, is all about applications of exponents, and there's quite a few of them, and there's some listed on the page there. We want to be able to use them, we want to be able to model things with them, we all want to be able to solve and work with them and that sort of thing. This here, this end goal, you're not ready to do this yet, or you may be, I guess, but this end goal is an application. Okay, carbon-14 dating. If you've ever looked at carbon-14 dating, you know how it's they use it to date fossils. Carbon-14 does decay into a different element. The relationship between the carbon-14 and that can be calculated using a whole bunch of science, and from there you know how much carbon-14 or what percent of carbon-14 is remaining. So from there you can get exponential equations. Now in this one here, I've already given you the equation. Carbon-14, radioactive isotope of carbon, has a half-life of approximately 5,730 years. The percent of carbon-14 remaining is given by this equation. An anthropologist discovers that 40% of the carbon-14 is still there. How old is the fossil? So the anthropologist or somebody involved with the anthropology can go and do the calculations. You know the percentage remaining is the 40, so that's P, and it equals, based on this equation, come on pen, this equals 100 times 0.5 all to the power of T over 5,730. Okay, now this is an application, this is an exponential function. Or an exponential equation. You've got to solve for this. There's a whole variety of ways to do it. What I'm going to do is divide by 100. So I'm going to get 0.4 equals 0.5 times t to the 5,730. Now from there I can do a log. So that's going to be the log base 0.5 of 0.4 that equals t over 5,730. So I can multiply the 5,730 up, and I'll get t equals 5,730 times the log base 0.5 of 0.4. And from there I can figure it out. I mean, that's a number, okay, but I don't know what that number is, so I can go and figure that out. And if I figure out 5,730 times the log base 0.5, okay, so I'd log base 0.5 of 0.4, and I work this out, I'm going to get that this sample is about 7,574 years old. Okay? And so you can go through and figure out, okay, well, if that's the situation and it's found in this area, what culture is it? You could also look at it in terms of like the things that are there, but it allows you to get an idea as to when that particular sort of culture and those particular sort of weapons or whatever the fossil is found with, when it was used, that sort of thing. Now, you can't do this yet, and I've got logs involved here, and you're wondering, what does it mean, log? I mean, I thought I put logs on fires. It's not what I'm doing. But nonetheless, that's the idea, that's what's going on. So that's where exponents and logs, it's trying to do these things, because there's a lot of scientific examples that work. Now, just so you're aware, a log or a logarithm, in fact logarithm is the right term, we tend to just use log. It's the opposite of an exponent, okay, the inverse of the exponent, and it allows us to break the exponent out, okay, and that's what we need to do. But because the logs are complicated and there's lots going on with them, we've got to figure out our exponent laws first, because the exponents and logs are related together, and so we have to be comfortable with exponent laws. So with the exponent laws, there's a whole variety of things. The first exponent law that you talked about, and the one that you know, looks like this. Okay? Exponent law number 1. If you have something to the power of x times something to the same base to the power of y, you keep the base the same, I'm just using the letter a, and you add the exponents, x plus y. This is the product of two separate logs. The product of two separate logs. You can add the exponents part together. and you can get that. Now, this allows you to do ones like this, x cubed, okay, e.g., x cubed times x to the fifth. You know that x cubed is 3x's times x to the fifth is 5x's. And so you figure that out. Well, what do I have? Well, I have 8x's, so I'm going to say it's x to the 8th. 3 plus 5 is 8. And it allows you to do those sorts of things, okay? If there's a coefficient in front, the coefficient just gets multiplied. So if I look at one like this, 5x to the 7th times 2x to the 8th, I multiply the coefficients, the 5 times 2 gives me 10. And the exponents, I keep the base the same, x, and I add the exponents, 7 plus 8. 7 plus 8 is 15. So I get 10x to the 15, okay? And that's that first exponent law. It's not a terribly difficult law. In fact, you've done that lots before, okay? But so you've got that. Now, the second exponent law, okay? And I'm just going to move my paper because I need some blank paper. The second exponent law is almost identical, just instead of multiplications, it's divisions. So if you look at law number 2, okay, law number 2 is this. You have a to the power of x divided by a to the power of y, okay? And if you have the divisions, you just keep the base the same, a, and you do x minus y, okay? You just subtract. Now, if it is in a fraction, it is ending up in the numerator, so that's just how it always works. It always ends up in the numerator. But it allows you to do a whole variety of things. We've looked already at things like this, e.g., if I have x to the 12th divided by x cubed, okay? What is that going to be? Well, you can use the exponent law, keep the base the same, and 12 minus 3 is 9, okay? That's one way to look at it. Before, what we did was this. There were 12 x's. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm cursing the fact that I made the number so big. Over, okay, 3 x's in the bottom. 1, 2, 3. What cancels? Well, 1 x in the bottom cancels with the one on the top, ditto, and ditto. I cancel 3 times. What am I left with? These x's. How many are there? Count them. There's 9. So I'm going to have x 9 times, or x to the power of 9. It's still the same thing, okay? Keeping in mind when you do the divisions, the same thing happens. So if I do one like this, if I've got a coefficient in front, where I say something like 10x to the 5th over 4x to the 7th, or 4x cubed, maybe, let's say that, okay? In this case, I've got 10 divided by 4. Now that's a fraction. I can't do it. So I'm just going to say, what can I divide top and bottom by? I can divide both by 4, so I'm going to get 5 in the top and 2 in the bottom. I just divide by 2, or divide by 2. Okay, I'm going to get 5. I'm going to get 2. Okay, so that's done. That's done the same way. There was x to the 5th in the top. There was x cubed in the bottom. In the numerator, I can leave it, keep the base the same. 5 minus 3. 5 minus 3 is 2, so I will get 5x squared over 2, and that's just what it works out to be. These exponent laws, nothing terribly spectacular. The third law I want to talk about, and I'm just numbering these, is the ones where you've got a monomial with an exponent in it, and you raise that exponent to another exponent. Power to a power, in other words. In this case, you keep the base the same, and you multiply the exponents. Okay? Now what's going on here? Well, you can look at it this way. Okay, if I have e.g. x cubed to the 4th power, what that means is I've got 4x cubed. So I've got an x cubed, I've got an x cubed, I've got an x cubed, I've got an x cubed. Okay? And if I take that and break that down further, x cubed is xxx, and an xxx, then an xxx, and then finally an xxx. What do I have? Well, I have a whole bunch of x's. How many? 12. So I can write that as x to the power of 12. And that always works, okay? The other way to do it is you just take x cubed to the 4th, keep the base the same, multiply the exponents. 3 times 4, 12. Same thing, okay? It just goes on from there, okay? Keeping in mind you can have multiple versions of this, e.g., okay? if I look at this. If I say I've got x squared to the 5th times x cubed to the 7th. Keep the base the same, 2 times 5 is 10, times, keep the base the same, 3 times 7 is 21. Now from here, I've done the power to powers, they're already done. Now I've just got the product of exponents. This was law number 1 from before. So law number 1, keep the base the same, add the exponents. 10 plus 21 is 31. Okay? You could write it out as a series of x's and go from there. It's just a lot of writing out. Okay? Same idea holds if it's division, it's the same thing. So I can have e.g. If I do x to the 5th cubed divided by x to the 7th all squared. You do the powers to power. So in the top it's x to the 5th cubed. Keep the base the same, 5 times 3 is 15. In the bottom, keep the base the same, 7 times 2 is 14. Now from there, you do the divisions. Okay, the division is keep the base the same, and it ends up in the numerator. 15 minus 14 is 1, so you get x to the 1, or just x, and you're done. Okay, so that's what it boils down to. It's just nice and simple. So you've got that sort of idea. Okay, continuing on with the exponent laws. Okay, there are lots of things that can happen with exponent laws. If I look at law, then the fourth one I'm going to do is the log of a monomial, or the power monomial to an exponent. So if I talk about number 4 is going to look at AB. There's two pieces, they're multiplied together. There's no plus or minus. But if I raise that to an exponent, okay, what I can do is I can take the first piece and raise it to that exponent, the second piece and raise that to an exponent. This is not the case if it's a binomial, okay? So what I mean by that is when you've got like x plus 5 squared, okay? When we were doing polynomials, we had this. This is a binomial. It does not, it does not equal x squared plus 5 squared. Because the thing is, this is a binomial. So this is wrong, okay? You've got that. It doesn't work that way. A lot of people like to do that, and the reason they like to do that is because they think, well, this exponent law works for everything. In this particular case, this has to be a monomial. There's no plus or minus. There isn't separate terms. Then I can do this. And what it allows me to do is ones like this. E.g., if I say bracket 5x, close bracket, cubed, okay, then that becomes 5 cubed plus x cubed. And 5 cubed, you have to go into the calculator probably, is 125. X cubed is just x cubed, and it becomes that. Okay? It's one of the reasons why in the calculator things get confused. If you want to square -7, you have to put it in brackets. And what the calculator will do is very accurately go -1 squared times 7 squared. -1 squared is +1. 7 squared is 49, and it will give you +49, which is the correct answer. If you don't put the brackets in the calculator, okay, I'm just going to write calc, question mark, question mark. If I just write -7 squared, then what that is -1 times 7 squared. That's what this is. So -1 is -1, 7 squared is 49, -1 times 49 is -49. So this is the error, if this isn't what you want. Okay? Now if this is what you want, and it's pretty rare that's what you want, but if this is what you want, then you're all good. But it has to do with this exponent law as to why that ends up not working out properly. Okay? And you can do a whole variety of examples. Okay? Getting quite a bit harder here, I could look at this one. I've got 8x all squared times 5x all cubed. Okay? So in this particular case, because these are monomials, I can distribute it in, so it's going to be 8 squared x squared, and this is going to be 5 cubed x cubed. 8 squared is 64x squared. This is going to be 125x cubed. And then I work that out. Multiplying the coefficients, 64 times 125. I go do that. That is, according to my calculations, 8,000. And I've got an x squared plus an x cubed. Keep the base the same. 2 plus 3, 5. That's what I end up with. Okay? And I can make it as complicated as I want. Okay? I can do all sorts of things. Looking at ones like this, e.g. Okay, I've got 2x to the fifth. Okay, all in brackets, no exponent. Okay, but here I've got 3x squared and then cubed for the whole thing. So in the first one, there's no exponent to an exponent. So that's good. That's happy. I'm good with that. In this case, it's 3 cubed times x squared cubed. X squared cubed. Okay, now you can write that out. Keep the base the same, and you multiply the exponents. Okay, I'm going to write the whole thing just to make sure that it makes sense. So going through with this, 2x to the fifth, I still haven't done anything with that, I'm just rewriting it. Okay? In this second one, and I'm stuck by the paper now, I'm trying to push it up. In this second one, 3 cubed is 27. X squared cubed is going to be x to the 6. And then from there, now everything's cleaned up. Now I can multiply these pieces together. Now keep in mind the coefficients you just multiply. 2 times 27, that's 54. X to the fifth times x squared, keep the base the same, add the exponents. 54 x to the 11th, and that much is done. That's the fourth exponent law. Okay? The fifth one that I want to talk about here, and I know you're getting tired of listening to me already. The fifth one is the exponent, a fraction to an exponent, a over b to an exponent. Okay? If you have that, okay, it's still a monomial, so each piece, it's a to the x over b to the x. It's very much similar to the last one. Okay, you get the same idea. So in this case here, starting with a harder example, if I have 3x squared cubed over 2x all to the fifth. Okay, so I've got those things there. Now I've got lots of options to do this. Here's how I would do it first. I start with cleaning up this. Okay? And what I'm going to do is I am going to get 3 cubed, x squared cubed, which is x to the 6, over 2x. And all of that still to the power of 5. Cleaning that up, I'm going to get 27 x to the 6th over 2x. And still, that's all to the 5th. I've cleaned that up. Now from there, I'm going to put the power of 5 in. So what I'm going to end up with is 27x to the 6th to the 5th power divided by bracket 2x, close that bracket, to the 5th power. Okay. Cleaning this up, that exponent goes in, so it's going to be 27 to the 5th power. X to the 6th to the 5th, keep the base the same and multiply, x to the 30, over I'm going to get 2 to the 5th times x to the 5th. So I'm happy there. Okay, keeping in mind what I am going to get, 27 to the power of 5. It's 14,348,907 according to my math. Okay, I'm going to get x to the 30 over 32 x to the 5th. Let's see if I can reduce this number in front, the coefficients. Okay, so 14,348,907 divided by 32. See if it reduces as a fraction. It doesn't. So now I'm going to keep the base the same here. Remember, I'm doing that final division. So I have 14,348,907 in the top, 32 in the bottom. Keep the base the same. It goes in the numerator. 30 minus 5 is 25. And there is my final answer. Okay? So you've been using these exponent laws, and there are piles of examples of this sort of thing. Okay? And once you're comfortable working with the exponent laws, you can do anything. Okay? The key is remembering that you use the order of operations. I usually start looking at this one, because this one was hard. Starting with this one here, I start in the middle and I start trying to clean it up first. You may have cleaned it up more first, it's your call. However, I usually try to clean it up, then I try to put the larger laws in, that sort of thing, okay? So you've got the exponent laws. Now in class I'm going to do a whole variety more examples. I'm not quite done, but that's what's going on. Now negative exponents, okay? With negative exponents, with negative exponents, old-fashioned reasons you don't want negative exponents, okay? You couldn't do it. It doesn't take long. You go back in history, calculators couldn't do them. Doing them by hand was nearly impossible. Slide rules couldn't do them. So before we had this advanced computing technology, we couldn't do negative exponents. But since they occurred in a whole variety of situations, they had to look at what's going on with negative exponents. And once they looked at that, they realized that negative exponents, there was a simple law. And so once they got comfortable using that, they ended up making this rule that, well, we just don't want negative exponents because we can't deal with that. Now, it's a throwback, okay, there's no question of that. It doesn't matter so much anymore. But at the same point in time, you've got to remember that you can't have negative exponents, okay? And so that's what we're doing. Now, for old-fashioned rules, it's there. You either have, if it was a negative exponent in the top, okay, because that was that over 1, okay, you flipped that down and it became x to the positive a. Okay, that's an a, not a 9, that's an a. Or, if it was a negative exponent in the bottom, we flipped it up and it became x to the positive a. Okay? All the other stuff, whether it's 1 or whatever, all the other stuff just kind of stayed where it was. It was the negative exponents that moved. So if you were trying to work with this, e.g., 3x to the negative 5, and you want to get rid of the negative exponents, well, it's this part here that's the problem. The 3 is no issue at all. The negative exponent is the problem, and that has to flip down. When that flips down, okay, it becomes the denominator of a fraction. And instead of being x to the negative 5, it's x to the positive 5. So it's flipped down. But now, what's left in that numerator? And it's the same as it was before. If you can't see anything, it's just 1. This one still has the 3, though, in it. So it became 3x to the negative 5, which does give you a non-permissible value. X can't be 0, all that sort of thing. But I'm not worried about the NPVs. Okay? So you get these sorts of things. Okay? Going the other way works just as well. If I had 7 over x to the negative 4, okay? If I had this is all well and good, except for the fact you can't have that negative exponent. So it has to flip up. You're just flipping that portion. Okay? So now the x to the 4, it was negative 4, it's now going to be x to the positive 4, it's in the numerator. There still is the fraction line. There's nothing visible, or a 1, okay, underneath. In the numerator, that 7 is still there, so you get 7x to the 4th all over 1. You don't need to write the over 1, but it's there, 7x to the 4th, okay? Now it still has its non-permissible values, keeping in mind, though, I'm not worried about it, okay? So continuing on, okay? You can look at these, okay? E.g., here's an example, and we looked at things like this a long time ago. 2x to the 5th over 3x to the 8th. Now you can look at this as we did before. Okay? And as we did before, it was 2 and then 5x's over 3 and 8x's, 1, 2, 3, 4, 5. In the top, you're left with the 2. In the bottom, you're left with 3. And then x cubed. And so you were done. That was before. That's what we did. Now that you're understanding or you remember the exponent laws, you really could, and there were some people in classes that made this case. I do this, 2 divided by 3, can't do that. So now I do leave it as 2 divided by 3. X to the 5th divided by x to the 8th is going to be x to the negative 3, which then has to be flipped down. Okay? It's up to you which one you prefer. But there were a lot of people making these cases before. So then that x to the negative 3 flips down. It becomes x to the positive 3 in the top, or in the bottom. The 2 is still in the top, the 3 is still in the bottom, and you get the same thing. Either way, it's the same. Okay? It doesn't matter how you do it, it's the same. Okay? And so you get to play with all sorts of different ones. If I do another example just really quickly, e.g., I'm going to have 5x squared, okay, over 3x to the 5th, 2x to the 7th. Okay, and I'm working this out. Now I try to keep it going. Keep in mind I'm not worried about the NPVs. In the top it's 5x squared. I'm just going to leave it. In the bottom I got to do some work. 3 times 2 is 6. X to the 5th times x to the 7th. Keep the base the same. Add 7 plus 5 is 12. I'm there. Now if I try to do this, the 5 and the 6 don't simplify. X to the 2 divided by x to the 12th. The 5, the 6 stay. Keep the base the same. It goes in the numerator. 2 minus 12 is negative 10. There's your answer. However, the negative exponent is the issue. Okay, so that negative 10 has to flip down, that exponent. Okay. You would end up having 5 over 6x to the 10th. However you do it is fine, but that's the sort of idea. And all that happens is I make these more and more and more complicated. Now keeping in mind, in class I'm looking at more examples, so I'm going to spend more time looking at examples, but this is the basic idea. Your homework is a worksheet, worksheet 1. You can download that off the internet. Otherwise, I hope that makes sense. Best wishes, and we will see you again.